Alright, so now let's look at this problem over here, and I pretty much call this the Hess's law for rate constants. I honestly don't know what it's actually called, what this topic is called. I just think of it as Hess's law for rate constants because it's pretty similar to Hess's law in that you have to sort of cancel out some of these molecules in order to get to your equilibrium constant. But with finding the equilibrium constant, this is going to be more different than the normal Hess's law for like enthalpy, because when we multiply, we're going to have to put that number to the power of. When we divide, then we're squaring or putting that, whatever we divided by, to the root of that number. And when we're adding these rate constants, we're multiplying them. And when we reverse these rate constants, instead of putting a negative number, it's 1 over the rate constant. So let me actually write some of these parameters over here. So if we multiply, and I would say multiply by n, then that goes to k to the power of n. And if we divide by n, and n is just like some arbitrary number, then that will go to the square root of k to that n power. If we reverse k, or we like switch it over, then that's going to turn into 1 over k. And if we add, and let's just say we add k1 plus k2, then that's actually going to be k1 times k2. So when we're adding all of these up, we're actually multiplying them instead of just adding them like normal Hess's law. So now that we know that, and pause this video just to get this in your notes, and because this is actually very important to know when we're going through this problem. And once you do, we're going to start with this problem. So this is our final reaction over here. So when I'm going through these Hess's law type questions, I really want to look at my final reaction and see what's on the reactant side and what's on the product side. So over here I have CH3CO2H on my reactant side for K1, and it's the same on the last reaction, on the final reaction. So I want to leave that the same because I need to leave this in the reactant side in order to create my final reaction. So I'm going to leave this here. Same for NH3 because I want to leave this on the reactant side, because at the end it's going to be on the reactant side. That ammonia is going to be on the reactant side. So I'm just going to leave it here as well. But let's look at this one right here. So our intermediates, or some of the things I see that we're just going to have to cancel out, are H2O2, or H2O, not H2O2. So we have water, we have hydronium, and we have hydroxide, which we need to cancel out. So the only way I see of canceling this out is reversing this reaction. So if I did that real quick, just reverse this reaction, moving this over here, and I reverse this entire reaction, then over here my K3 isn't going to be 1 times 10 to the negative 3 anymore, because my new K3 is going to equal 1 over 1 times 10 to the negative 13. And let's see what that gets us. So it's 1 over 1 times 10 to the negative 13. So that gets us 1 to the negative 13. So our new K3 is going to be 1 times 10 to the 13. So we can't use this anymore because we just reversed the reaction, and our new K3 is going to be this one right here, because we had to do 1 over 10 to the negative 13 because we reversed the reaction. Once we've done that, then we could pretty much eliminate all of our molecules, our intermediates. So this is going to go away, this is going to go away, 2H2O, 2H2O, both cancel out. Hydronium is on the product side over here, hydronium is on the reactant side over here, they cancel out. And hydroxide is on the product side over here, hydroxide is on the reactant side over here. So those cancel out as well, and we are left with our final reactant over, or our final reaction over here. Because when you add these up, when you add CH3CO2 plus NH4, that just gets you, I don't even know what this compound is, but it gets you that compound. And when you basically add these up, and since we're trying to add up these, since we added up all of our final molecules, we're going to multiply each of these Ks. So that'll be 1.8 times 10 to the negative 4, 1.8 times 10 to the negative 4 again, and then 1.0 times 10 to the 13. Multiply all of those, so that times that, and that should get us our final K. I'm just going to denote this one as KF, and that equals, let's put into sig figs, 3.24 times 10 to the 1, 2, 3, 4, 5, 10 to the 5. So that is how you find your rate constant going through these Hess's law type questions, because I just pretty much think of them as those Hess's law type questions. And all we really did was reverse this last reaction over here. So that turned into 1 over 1 times 10 to the negative 13, which goes to 1 times 10 to the 13. And when we multiply all of those, and I'm just going to double check my math over here, times that. Yeah, so we get 3.24 times 10 to the 5, and that is our answer for the final equilibrium constant, or the final rate constant that we have.